Welcome to this topic of the Demystifying IPv6 course on the IPv6 header structure. This topic on the IPv6 header structure is just one of many topics in the Demystifying IPv6 course. But before we get to the IPv6 header, the question is, how do we know when we receive a frame that there is an IPv6 header to begin with? So as you're probably aware, an Ethernet frame has an Ethernet type field, which we've been used to looking at the value of 0800 for IPv4. The value for IPv6 is hexadecimal 86DD instead. So now that we found the IPv6 header, let's compare the version 4 to the version 6 headers side by side. So these pictures are interesting because you can see at a glance the things that are the same and the things that have changed. Right away it should be obvious that the IPv4 header is more complicated. It has a lot more fields, hence the fields in orange have been omitted for IPv6. The fields that are the same are the ones that are in yellow. The fields in blue are basically the same, but their name and positioning has changed within the IPv6 header. And finally, there's one field that the IPv6 header has added called the flow label. It's also obvious comparing side by side that another difference between the IPv6 header and the IPv4 header is the IPv6 header is a bit larger, which makes sense as the address space is increased from 32 to 128 bits. So I'm going to build out this slide with some bullets to go over in more detail the changes between the IPv6 and IPv4 headers. First of all, the IPv6 header is a fixed length of 40 bytes, whereas the IPv4 header was always considered a variable length, 20 bytes minimum, but 20 plus bytes if it also included options. IPv4 options now have become IPv6 extension headers, which are not considered part of the fixed length IPv6 header, and they're more easily to recognize by the forwarding devices in between. Since the IPv4 header was variable, there had to be a header length field that was indicated as to the size of the IPv4 header for any particular packet. Of course, IPv6 does not have that worry with a fixed 40-byte header. The IPv4 total length becomes the IPv6 payload length, and one big difference there is the IPv4 total length also included the size of the IPv4 header, whereas the IPv6 payload length only includes the information following the fixed 40-byte IPv6 header. The IPv4 precedence and TOS bits, type of service bits, become the IPv6 traffic class field. Actually, both of them today use differentiated services for their definition. IPv4 flags and flag offset have been eliminated. The IPv4 flags were mostly used for fragmentation, which that concept has changed a lot in the IPv6 world as it is today, and we'll talk more about that later. The IPv4 time to live field now becomes the IPv6 hop limit. Originally, the IPv4 time to live was thought to be like clock ticks or seconds as the packets traveled through the network and the seconds ticked away, where it was considered impractical to keep track of time in that manner in a live network. So the hot limit concept is also the way that IPv4 thinks of it today. The IPv4 protocol field becomes the IPv6 next header field. So as I was talking earlier about IPv4 options becoming IPv6 extension headers, the next header field indicates directly that's the case, or IPv6 next header values also coincide to the IPv4 protocol values. For TCP and UDP, for example, a value is 6 and 17 respectively. The IPv4 header checksum is eliminated. When IPv4 was designed originally, the links were considered very unreliable, even to the extent that they might corrupt the IP header. So with IPv6, the links are considered more reliable, and therefore a checksum is not required over the header. Of course, the address is increased in size from 32 bits for IPv4 to 128 bits for IPv6. So overall, the address length increased by 4 times, but the header length only doubled. So IPv6 extension headers are handled more efficiently and give more flexibility with IPv6 than the old options did with IPv4. So the implementation enables IPv6 header to be a fixed length of 40 bytes. From a flexibility standpoint, it allows them to support more common functions using a specific structure of fields. Also, from a flexibility standpoint, they could also support future functions using options that are TLV encoded, type length value encoded, that will give more variable type of information to be provided with IPv6 extension headers. And if included extension headers appear one after another following the main header. So as mentioned before, the IPv6 header is a fixed 40 octets in length, and then that could be followed by one or more additional headers as indicated by the next header field. The next header field can actually indicate that a header following is an extension header. So with IPv6 and using the next header field originally from the IPv6 header, and then from each extension header has a next header field, they could actually be pointing one after another, and they could be chained along indefinitely. Whereas IPv4 had a fixed internet header length field which limited the options that could be carried in an IPv4 datagram. IPv6 does not have that same limitation. Of course, ultimately there could be an upper layer protocol that is carried by TCP or UDP, and so the final next header field would point to either one or to two. So here's an example of extension headers and how they're implemented with IPv6. So in the top datagram, you just have an IPv6 header followed by a TCP header with some TCP segment data from an application. So the IPv6 next header field will just have a value of 6, pointing to the TCP header as the next header in line. Whereas the datagram on bottom actually has a couple of other extension headers that are chained in between the original IPv6 header and the ultimate application data, the TCP header followed by the TCP segment of data. So one thing I mentioned earlier to make this more efficient for processing by intermediate devices such as routers is, instead of trying to reverse engineer via the internet header length and then having to parse for additional options in every packet, as was the case with IPv4, a router in between, if it has to process a next header as an intermediate device, then the original IPv6 header will just have a next header value of 0. I'll get into what next header values actually mean in a moment, but that's one way that a router knows exactly if it has to do something else with the packet than forward it. So the extension header types are mentioned on this slide. And extension headers, if present, should be in the specific order and only appear once in each datagram, with the exception being the destination option header may actually appear twice, near the start where an intermediate device might process it, and at the end where the ultimate destination device would process it. So of course you start off with the IPv6 header, and if there is a next header value of 0, that means that there's a hop-by-hop options header that an intermediate device such as a router would have to process. There was a next header field of 43 which indicated a routing header, but that has been deprecated as per RFC 5095. There could be a fragment header, next header value 44, as described in RFC 2460, but a key concept with IPv6 that only the end devices will fragment packets. Whereas with IPv4, the intermediate devices, the routers would actually do the fragmentation. So if any fragmentation has to occur, it would be done by only the source host, and then each individual fragment carried as whole throughout the network to the ultimate destination, which would put it back together. For IPsec, there is the encapsulation security payload header, next header value 50, and the authentication header, next header value equals 51. And these were described in RFC 2406 and RFC 2402 and apply to IPv6 as well. And again, there could be a destinations options header, next header value of 60, followed by either no next header, which has a value of 59, or some upper layer protocol. So again, next header value is 6 or 17 for TCP and UDP respectively. And finally, as indicated by the last blue on this slide, the hop-by-hop options are normally examined by all intermediate devices and is used to specifically convey management information to all routers within the route. So just another view of the extension header types in a table format in both hexadecimal and decimal values. One thing that you should get used to seeing with IPv6 is the next header value of a decimal 58, which is near the bottom of the screen, and that's the value for ICMP version 6, or Internet Control Message Protocol version 6, as we're going to find out in a different topic in this series of the Demystifying IPv6 course. ICMP version 6 is used for a lot of processes with IPv6. So this slide is pretty wordy. It's just explaining some information about IPv6 extension headers, such as what hop-by-hop options are used for. So it defines an arbitrary set of options that are intended to be examined by all devices in the path from the source to the destination, which are actually encoded in TLV format, so they can provide multiple functions, either current and or in the future. So there's a routing extension header, which provides the methods to allow a source device to specify an exact route that the datagram should follow. I mentioned earlier about fragmentation headers, about how fragmentation would only occur at the ends and not in the middle of the path that the packet was traveling. So there's a fragmentation header that will provide that function. There's also the encapsulation security payload and the authentication headers for the IPv6 protocol. And as I mentioned earlier, because of the end-to-end nature of IPv6 and not using any private IPv6 addresses or natting in between, it does provide end-to-end security capabilities. And finally, the destination options, which also provide an arbitrary set of options, i.e. TLV encoded, that can be examined by the destinations of the datagram. So this gives an example of the IPv6 routing extension header, although this particular extension header has been deprecated by RFC 5095, so I'm not going to be discussing it any further here. This gives an example of the fragmentation header, and just like all extension headers, it starts with the next header value, so it could be pointing to the next protocol or the next extension header in line. There are some fields that are reserved and that are used for a fragment offset. Similar to IP version 4, when a packet gets fragmented, the identification bits are the same for all the fragments, but then the fragment offset indicates where that particular fragment goes when trying to reassemble the larger packet. And so there are the more fragment bits that will indicate that when it's set, that means there's more fragments to come, but when it's 0, it indicates the last fragment in the message, so the destination device can begin putting it back together. So as an example of fragmentation, you have the unfragmentable part, and that would be the IPv6 header. And then you have the fragmentable part, which would be all the other data that was following. As you can see, the fragmentable port can be broken up, and then the fragment extension header would be inserted in between, and using the fields such as the ID and the offset, it would know which fragment is which in terms of fragment 1, fragment 2, and then using the flag bit, it would know when the last fragment arrived. So as I mentioned earlier, and in other topics, that IPsec is defined as part of IPv6 is essentially identical to the same implementation of IPv6 with IPv4. So as I mentioned, with IPv6, IPsec can be truly deployed end-to-end. So via the Internet Key Exchange, Authentication Header, and the Encapsulation Security Payload, that IPsec is implemented also within IPv6. I mentioned earlier too, hop-by-hop and destination options used to carry arbitrary information. In other words, they're TLV encoded, type link value, to provide maximum flexibility, and that's implemented as an extension header within the IPv6 world. So hop-by-hop options are actually implemented using two extension header types, the destination options. So these are options that are intended only for the destination, the datagram, or perhaps a set of routers in between if specified in the routing header. And hop-by-hop options, which contain options to carry information for every device, i.e. router, between the source and destination. And so you can see how hop-by-hop and destination options are formatted. So you can have one or more actual options inside each extension header. And then these would be encoded as a type, a length, and a value, and they can be strung along. So in other words, they're TLV encoded. And this gives you an example of some of the encoding of the option type field. There's a couple of bits that are used to specify the action upon receiving an unrecognized option, whether or not the option can be changed, and then finally the remainder of the option type. One particularly interesting hop-by-hop option extension header is Jumbograms, which are specified in RFC 2675. The IPv6 payload length is 16 bits, and that would allow you to support up to 65,000 bytes in an IPv6 packet. However, if we want to send packets larger than that, the payload length in the IPv6 header will be set to 0 and indicate that it carries a jumbo payload option. That allows Jumbograms to support up to 4 gig in length of packets because it uses a 32-bit jumbo payload length field. Of course, you have to have link MTUs that will support that in an end-to-end manner. So that will provide for more efficient transfer of data with fewer interrupts to the communication hosts, so they can process one larger packet than a large number of smaller packets. There's also changes that would need to take place to support Jumbograms with the TCP and UDP protocols. So UDP packets longer than 65,000 bytes may be sent by setting the UDP length field to 0. With TCP, an MSS of 65,000 bytes is treated to be as infinity. So when we're talking about IP headers and comparing the process of those, we consider it in terms of the critical router loop. So the critical router loop is a set of instructions that must be executed to determine how to forward a packet. So let's compare that with IPv4 and IPv6 on the next two slides. As we'll see in a moment, the IPv6 header is a reduction in the critical router loop. In other words, they're easier for routers to process. There's a lot of things that the routers don't have to do that they did have to do with IPv4, such as recalculate a header checksum, perform fragmentation, or process options that are not intended for them. So looking at the IPv4 critical router loop, the items in red on this slide are the negative aspects of processing an IPv4 header, additional processing burden that we place on the routers that we don't necessarily have with an IPv6 world. One thing you'll also know here is there are 8 steps total compared to, on the next slide, we'll see that there are only 6 steps in processing an IPv6 header. So starting with number 1, an IPv4 router had to process the IP header checksum field and determine if it was good or bad. And if it was bad, it would have to throw out the packet. It would next verify the value of the version field that it was for. It would next decrement the value of the time to live field. And if its new value was less than 1, so any router that decrements the time to live to 0 would actually have to throw out the packet and send an ICMP-v4 time to exceeded message to the source. The next thing we have to do is check for the presence of IPv4 header options, and if present, process them. Remember, it has to reverse engineer from the internet header length field that it's larger than 5, for instance, and then parse the option to determine if it was actually something it had to do about it, whether it had to or not. And then next, it used a destination address field to determine the forwarding interface and its next hop. And of course, if a router is not fine, send an ICMP-v4 destination and reachable message to the source. It would also have to potentially perform IPv4 fragmentation, meaning the output MTU, maximum transfer unit, is smaller than the actual packet itself. Or if the DF flag was set to 1, it would have to send an ICMP destination unreachable fragmentation needed and a DF set message to the source. It would then have to recalculate a new headers checksum and place its new value in the header checksum field. And finally, it would forward the packet by using the appropriate forwarding interface. Compare that with the IPv6 critical router loop. So you'll notice 1, instead of 8 steps, there's 6, and 2, that there's a few green fields here now that were actually easier to do now with IPv6 than they were with IPv4. So in both cases, we have to verify that the value of the version field, in this case it needs to be 6, and also decrement the hop limit field. And still have to send an ICMP time exceeded hop limit exceeded message to the source if it decremented it to 0, but at least it didn't have to recalculate a checksum based on that as well. It would check the next header field for a value of 0. Again, instead of having to reverse engineer from the internet header length and then parse options that were not intended for it, if the next header field was specifically set to 0, then it would know to process the hop-by-hop options header. Next, it would use a destination address to determine a forwarding interface in a next hop. And similar to IP version 4, if a router is not found, it would have to send an ICMP-v6 destination and reachable message back to the source. With 5, rather than performing fragmentation, if the MTU of the forwarding length is less than the IPv6 header plus the value of the payload length field, all it would have to do is drop the packet and not fragment it. Of course, it would still have to send an ICMP-v6 packet to big message back to the source. And again, finally, it would forward the packet by using the appropriate forwarding interface. Thank you for taking the time to view this topic on IPv6 header structure of the Demystifying IPv6 course.